You may be familiar with computers as devices that store collection of programs like files or graphics, right? Now, in this lecture, we will shift our perspectives to something different here. We will look at computers as billions of two-state switches. Consider this as light switches. These are the this means off and on, right? We will look at computers as billions of two-state switches managed by the control unit. Control unit in this case, let's say it's you that controls this, right? Now, in the previous lecture, we explored how computers communicate with the outside world using input and output systems. Now, we will investigate how computers encode and store data in memory. And we will write a C programs to reinforce these concepts in next lecture. Everything your computer does, from streaming a video to compiling a code like this, relies on a billions of two-state switches working together to make some sensible data, right? Each unique configuration of switches represents a specific state. Describing these states in a plain language will be tedious, so instead we use the numeric representations instead of writing like on or off, but you will see on or off representations of 1 and 0 in some examples. Basically, on here is 1 and off here is 0. It's like a light bulb. So this is a light bulb. Sorry for my drawing skills here. So light bulb does not have a light, so this is off. And if the light bulb is on, then it shines, right? So this is basically on, right? This has the same logic. And at the core of every computer, there are billions of microscopic switches called transistors. Now, each transistor can exist in one of two states, on or off, right? Which on means electrical current is flowing, off means it's not. And these two states represents the most basic form of information, the ones or zeros. This is why computers use the binary system. Now, we call it the binary. And now, how we write binary is to make it more understandable. For example, 1101. Now, this is a binary number. Each activity you perform on a computer, whether it's playing a song, writing a document, or browsing a website, this boils down manipulating combinations of ones and zeros, right? Now, what is a bit, you may ask? Now, a bit is the smallest unit of data in a computer. Now, the word bit comes from binary digit. It, b. And bit, the word from binary, the bit comes from binary digit. A bit, as I explained, can be 1, which is on, or 0, which is off. However, a single bit is too small to represent useful information, so computers group bits together to make some sensible information that makes sense, right? So 8 bits equals 1 byte, right? Now, a byte is big enough to store one character. Oops, sorry. Yeah, a byte is big enough to store one character. Can you see the screen? Yeah, that's perfect. So we can store characters inside 8 bits, which is 1 byte. So what can we store? For example, A. We can store single A, single B, or like single C, D, question mark, right? And the pattern of 8 bits in ASCII representation of the letter A, how can we do that? Is A here is 0, 1, 0, 0, half byte, and 0, 0, 0, 1. So it's always advisable to write bits and bytes in a 4 format. And yeah, that's basically it. This is A in a binary representation in ASCII representation here. So why computers use binary at all? Now, binary is ideal for electronics because it is simple and stable. Now, there's three main reasons here. The first is electrical efficiency. Two voltage levels, like 0 volts and 5 volts, are easier to distinguish than 10 different levels, right? So 0.5 volts. Yeah, this is another form of information which you will learn later. But yeah, that's basically it is efficient. Or it could be like 0 volts or 3 volts or 1.3 volts, which I strongly believe that if you have got into your BIOS settings, there's an choice that you can make the options on the 1.3 volts or 3 volts. And yeah, that's basically the most efficient that computers get right now. And it has error resistance. So binary signals are less likely to be corrupted. It is either 0 volts or some volts, like 3 volts or 5 volts, right? And it is simple. So circuits built for two-state logic are more reliable and easier to design. Now, as humans, you know that we use decimal. Decimal, yes. So if you don't know what decimal is, decimals is the basically base 10, which we use like 10, right? Or 296 or 390 or 1000 5, right? This is our number system that humans use. But binary, which is base 2, is perfectly suited for hardware. So all modern digital computers use binary under the hood. And there's another nice thing we have, which representing large binary numbers in a hexadecimal notation. And as you have seen so far, binaries, binary numbers can get very long very quickly, right? So for example, 0 or 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, and 0, 1, 1, 1. Now, this might look much, but compared, this basically means two characters in ASCII here. Now, this is hard to read and prone to mistakes, and that's where hexadecimal helps. Now, hexadecimal, which is, let's say, the hexadecimal, or hex, is a base 16 number systems. So it uses digits from 0, I will also take note this, so from 0 to 9 and letters from A to F, or uppercase A to F. So uppercase and lowercase doesn't matter here, so you can write both ways. It is either uppercase or lowercase. In computer language, it doesn't matter at all. And one hex digit can represent 4 binary digits. So here, this is basically a 1 hex. So as I said, 1 hex character can represent 4 binary digits. In this case, it is 4 hex, right? In this case, it is 4 hex. So each one is 1 hex, hexadecimal, 1 hexadecimal, 1 hexadecimal, and 1 hexadecimal. So why use hex at all? Hex, as you have seen so far, is easier to read, has a shorter representation, and it is common in debugging and programming, as you will see in next lectures. So basically, this binary here, 1101, we'll use different color, means B in ASCII. And for example, 0110 is 6. And 1010 is A. Or yeah, kind of right uppercase. And yeah, we have 0111 is 7. By the way, don't make mistakes here. These are all hex. Hex. This is not a word here. This is a hexadecimal representation, right? And this is not a number. This is a hexadecimal representation. Don't make mistakes here. This is hex 2, and this is hex 2. So if you see 7p in debugger, what does this mean? 7b translates to 70111, and p is 1 1 0 1. Yeah, that's not so hard, right? And also, for example, B6 here translates into B is 1 1 0 1 and 0 1 1 0. Or for example, 6 7 translates into what? 6 7 translates into yeah, 0 1 1 0 and 7 here 0 1 1 1. So these are not words, I will remind you. These are just a hexadecimal representation of bits here. And you can use the tools like calculator applications or online converters to help while learning this.